organic ions may not always be carbocations or carboanions. They can actually be radicals. That's where a carbon atom has a single electron. Let's take, for example, a benzylic radical to illustrate this idea of resonance in radicals. So this is a benzylic radical. So there is a single electron, you could see it, that single electron on carbon, which is the alpha carbon or the alpha position. We can actually stabilize this by resonance, and we can do that by indicating electron movement, but this time not using the normal arrow or the arrow that's used to indicate movement of two electrons. Now single electrons move, so therefore, if you like, a single head, if you like, or half-headed, if you like, the arrow, that's how it should be. So we use an arrow of this type, therefore, something like that, which indicates movement of that single electron from carbon to the middle of that CC single bond or that CC bond. And now we need to bring a single electron from this carbon-carbon pi bond. So we break the carbon-carbon pi bond. We release one electron to where that single electron is going, and the other electron should go now to that position. So the pi bond of this carbon-carbon double bond has now been broken, but it has been broken symmetrically. One electron has gone to that position to unite with that single electron in order to make another pi bond, and the other single electron has gone to the other carbon. By doing so, we can get another resonance structure for this benzylic radical. So something like that, where the radical has now moved to this carbon. You can see it. Yeah. Now we can continue to delocalize that radical, if you like, delocalize electrons, move electrons around as a result of breakage or breaking of carbon-carbon pi bonds, in this case symmetrically, because what we are talking about basically is radicals, so movement of single electrons. So we break this carbon-carbon double bond, we take one electron here, that single electron of course goes there to unite with that electron, and the other electron of that carbon-carbon double bond goes to the other carbon. So something like that is reasonable. Now we get therefore another resonance structure of this radical, and now that radical has moved now to that position as shown. We can continue to move electrons by moving this single electron now to the middle of that CC bond, breaking this carbon-carbon double bond, taking one electron to unite with that electron, and the other electron now should move to that position. So therefore we can get another radical. So something like that would be the result of this electron movement. So that's the produced radical, which suggests that radical at the benzylic position is actually stabilized by resonance. What's interesting here is the use of that special arrow to indicate, if you like, the half-headed arrow to indicate movement of only a single electron. Therefore, the benzylic radical is stabilized by resonance.